let's restart. So our next young researcher is Wallace Mangueira de Souza from UFPB, and he will tell us about discriminant, vertex, and general type of a family of polynomials. Please, Wallace.
I would like to thank you for the committee for the opportunity. The topic is discriminant vertex in general type of a family of polynomials. The structure is this one: motivation, family of polynomials, discriminant, vertex, and type, applications, and references. The motivation of this talk is the following. We have supposed to have a family of plane cubes, and assuming that the generic fiber is smooth, so you can take the dual of this generic curve. So we may ask, what is this limit? More precisely, we may ask which plane curve the dual curve to C star degenerates to as they approach to 0. In addition, we just don't know, we want to know to calculate this limit, and more, we want to know how many terms of this family of plane curves we need to consider to compute this limit. This problem is not new. The history goes back to the last 19th century, surfacing in works by Maillard and Zoeffen. They worked on computing these limits as a step in determination of characteristic number of plane curves. So to answer both questions, we use the method introduced by Katz. First, we localize in the open Z equals to 1 and assume the following structure. The special fiber is, this guy here, is this product of these irreducible components. And we assume that each one is decomposed in this some extension of this frac of A, and using the extension of the Poisson expression, we are able to compute this discriminant. This one will be a power of t times another discriminant, and its leading coefficient is what we were interested. So with this notation, Katz proved the following theorem, assuming that the family is regular, so this leading coefficient satisfies this expression here. And of course, using some, using the some change of coordinates, we may conclude the following. This term here, give us the limit of this expression. The another one give us the sum of the dual of each component. This another part give us this zero cycle, and the another one give us, I confusing this control. This is another part. And conclude his paper with this following remark. The techniques described here can be used to find limits of dual curves of non-regular degenerations on merely compute more terms in the formal Poisson expression. The result has the same form as in the theorem, a contribution for the dual of each component, a generalized formal part, and a contribution from each intersection. So with this remark, we are able to ask the following questions. How to determine the generalized formal part, and how many terms of this formal expression do we need? The first question is important because it's the missing part of the formal general expression of this limit. And the second part is equivalent to determine how many terms of f we need to compute this limit. So to answer the first question, we consider this following construction. We take the t rows of f using the expansion of Poisson with terms in A. We are able to decompose f in this way. So we change f nu by w. So the generalized formal discriminant with respect to f nu is defined by this one. So the generalized formal discriminant is defined as the formal discriminant of this polynomial. This polynomial with this variable. This is the constant term, the coefficient, if you wish. And this another part is the composition of W as product of rules. So this is the formal expression of the discriminant. And with this definition, we are able to to demonstrate the following theorem. So the only hypothesis that I need here is this delta is non-zero, that it's all the t roots are pairwise distinct, and also we recover the discriminant defined by Katz. So here we make the following remarks. This discriminant here is divided in two parts. The first one, a contribution from the dual of each component in the fiber special fiber, and the remaining part is what we call it by vertex. The vertex, we call it this term of vertex because this corresponds to the vertex of a plane curve in the family, since that C0 is the special fiber. Another thing that we have in mind is the following. Note that this term depends how many terms of f that you need to compute this delta prime 0 is equivalent to determine how many terms that you need in the family to compute the vertex. So the question 2 here is equivalent to determine how many terms that you need to compute the vertex. And the number is the general type as we see. We start taking the t roots of f and consider this number the order of this series here, and define the type of f with respect to this component as this one is equal to floor function of the exponent exponent of f times this number here. So theorem 2 says that if you take the maximal of this number, it's enough to compute the vertex of that family. That is, if you take just the tau first name of the family, it's enough to compute the vertex. So it's enough to compute the limit. And this number is called the general type. Now we compute some vertex and type with respect to some component of the special fiber and give the interpretation as zero cycle. We consider the family of the first kind, this terminology used by Zoyfen in that article that I had mentioned before. It's a family that satisfies this expression. We assume that this product is non-zero, and this component here is square free. So the type with respect to x is equals to 1, but since this is square free, we can say that the general type of this family is 1, and the vertex satisfies this expression. We compute the vertex using that formula that I mentioned before. And the general type is equal to 1, so we may write anything of order bigger than 2 here, that this limit of the dual point curve of this family does not change. So the vertex of this family is the interpretation of this formula is this one. The second type, we consider this equation here, where this component is square free again. The type with respect to x is equal to 2. And the vertex satisfies this expression. The interpretation as zero cycles is this one. But once more, since this component is square free, so we may say that the general type of this family is 2. So we may put or write anything here that the limit of the dual plane curve does not change. And the third kind is the same. And we have another family of plane curves that satisfies this expression. This family we may see as a generalization of the families of the first, second, and third type. And sorry, I just pushed by. This is the vertex of the family satisfies this equation. And we have this corollary from that theorem here. This corollary here generalize these both corollaries in this paper. And we finish this talk computing the general type of the several families of polynomials. Each one appears here in Kat's paper. Here are the references that I used, and thanks.